here we're going to talk a little bit about geometric similarity. Now, most of you are familiar with some results on geometric similarity. It's standard in high school to discuss similar triangles, for example. And those two triangles, for example, are similar if they have the same shape, but one of them could be much larger, one of them could be much smaller, but the two similar objects do have the same shape. And that definition generalizes to any objects. Objects are known as geometrically similar if they have the same shape, but they do not necessarily have the same size. And what we will do to detect similarity is look at ratios of corresponding sides. So let's look at these two examples. Let's take these rectangles. Let's take one with, these are rectangles, sides and ratios 7 to 5. And let's take one, maybe I should draw it, well, let's draw it on the whole board so I can draw it almost to scale. It's hard to draw exactly to scale. So let's draw them kind of to scale. We'll do two examples here, one where they are similar, one where they aren't. Example. So right here, 5 and 7. And let's look at this larger rectangle with sides in ratio, say, 21 and 15. So the question is, are these two rectangles similar? And what we will do to detect whether they're similar is look at the ratio of sides. So let's call this A, let's call this B. The ratio, we will take the sides on B and divide them by A just to remain consistent. We'll always do the second one divided by the first. So 21 and 7 correspond. Those two sides are the two longer sides on these rectangles. 21 over 7 equals 3. Okay? 15 over 5 also equals 3. Since these two ratios are equal, these rectangles are similar. So since these ratios are equal, these rectangles are similar. Rectangle's a long word, so I just drew a little rectangle and S. Now, if you had an example like this, let's say instead of 21, 15, let's say we had 21 and 10. Well, second example, are these two rectangles similar? Well, you would again do a length of sides argument, or a ratio of sides argument. The longer side here is 21, the longer side there is 7. 21 divided by 7 is 3. The shorter side on this rectangle is 10. 10 divided by 5 is not 3. I should have erased that 3 also. 10 divided by 5 is 2. So these rectangles are not similar. Now, similar shapes really are just one shape is larger than the other, but they have the same size. But it's larger in the same way in each direction. And we can measure that using these ratios. So in that first example, let's go back to the first example. Or in your notes, you can just write this as a remark next to your first example. This number 3 is called, in this case, this ratio, 3 is called the linear scaling factor. Linear scaling factor. And we're going to look a little bit more at that scaling factor, because similar objects are just objects that are scaled up or scaled down. If you did this as your second one and that as your first one, you would get 1/3 as your linear scaling factor. So let's compare the area of those two rectangles. Let's compare, let's compare areas. Let's compare the areas of those two rectangles. Well, the first one, we had 7 and 5. It's area of 35. That's not going to matter much right now. The second one, well, now let's do a different example, actually. Let's do one without that 3. Let's just draw one that I can draw more reasonably to scale. So this question will have 2 parts. 2 parts. Are these similar? And then look at their corresponding areas and how they relate. These 2 rectangles, well, to see if they're similar, let's compare sides. 14 over 7 is 2. 10 over 5 is 2. So yes, they are similar. Well, that's great. Now we're going to see how that 2 shows up in their area comparisons. Now, it might be difficult to see exactly how that 2 shows up if you just look at these areas as 35 and 140. It might be difficult. So let's compare the areas in a different way. Let's compare the areas by fitting these rectangles into this. How can we do that? Well, this is a 7 and a 5. We know that each of these sides is 2 times 7 and 2 times 5. So right here, we can break that 10 into a 5 and a 5. We can break this 14 into a 7 and a 7. So right here, we'll observe there's one of those rectangles. Each of these 4 rectangles is the same as this one. So we'll notice 4 of the smaller rectangle fit in the larger rectangle. So we'll notice 4 of the smaller rectangles fit in the smaller, or 4 of the smaller rectangles fit in the larger rectangle. Well, that's interesting. We recall that we had a scaling factor, a linear scaling factor of 2. 2 is 4 squared. 2 is also 2 times 2. So right now it's possibly ambiguous whether the scaling factor relates to the area using a square or just by a multiple of 2. Let's look at a second example. And then make that comparison. Example. How many square feet are there in a square yard? How many square feet are there in a square yard? Well, there are a couple ways of answering this. I think the easiest way is actually with a drawing. I like to see this, I find it easiest to see with a drawing. So let's draw a square foot. Here's a square foot. The square foot is 1 foot by 1 foot. Remember, a yard is 3 feet. So a square yard, here's our square yard. A square yard is 3 feet by 3 feet. And we'll notice, so notice, let's notice, where should we notice it? I'll notice it right under, and I'll notice it over here. That's how I was doing it before. Notice the linear scaling factor is what? 3 divided by 1 is 3. 3 divided by 1 is 3. They're both squares. Is 3 over 1, which equals not 1, which equals 3. We'll keep that in mind. because our goal is to compare the linear scaling factor to the scaling of the area. Well, how many square feet can we fit in here? Well, a square foot is 1 by 1. So right here we can divide this 3 into a 1, a 1, and a 1. We can also divide this other 3 into a 1, a 1, and a 1. So right here you'll notice right there is 1 square foot. There are 9 of them. So notice there are 9 square feet in a square yard. And we did that using a diagram. So right here we have that the linear scaling factor does relate to the area scaling. And in fact, the linear scaling factor squared gives you how the area changes. So here the linear scaling factor is 3, and the area went up by a factor of 9, which is 3 squared. So let's record that as a theorem. So here we have the area of a scaled up object goes up in proportion to the square of the linear scaling factor. And there is a notation for this. I will write it down. I won't use it too much. Is it that way or the other way? Yeah, it's kind of an alpha. It's not really an alpha. But if L is the linear scaling factor, then A is proportional to L squared. Now, we just looked at some examples to see how the area changes as we scale up. What happens to the volume as we scale up? Well, volume is a three-dimensional number. Area is two-dimensional, so we're going to need three-dimensional shapes. So the question is, how does volume scale? Well, let's take a cube. Let's make it some cube. Let's throw numbers on. Let's make it a 2 by 2 by 2 cube. And we're going to find how volume scales without actually taking any volumes. Before we took some areas, actually we kind of didn't with that. We avoided taking areas. We're also going to avoid taking volumes. This cube does have volume 8. That won't matter. Let's scale it up by a factor of, how about 4? Let's scale it up by a factor of 4. And let's draw that cube. So the cube will be, what, 8 by 8 by 8, and you can find the volume. The volume of that's 8 to the third, which is, what, 512, I think? Yeah, 512. But I'm not going to worry about that. I'm just going to draw a scaled up cube, and I'm going to have to draw it a little more toward the left because I want it on one board. So let's scale this up by a factor of 4. And in this cube, let's mark off these 2 by 2. So it's 8 by 8 by 8. So how many 2 by 2s are we going to fit in this? Well, this 8 by 8, we can divide into 2, 2, 2, and 2. So right here, now all of these are 2 by 2 squares. But we're also going to divide this in each dimension into 2 by 2 by 2. So right there on top, we divided that into 2 by 2 by 2. So let's divide this last face that we can see into 2 by 2 by 2. So right there, we've divided this all up into 2 by 2 by 2. And the question is, how many of these cubes are there? Well, to do that, let's just look at the top layer and then multiply by the number of layers. How many cubes are there on the top layer? Well, there's this one. Let's start over here. There's this one with these sides. So right here in that corner, there's one cube. Well, there's one. Here's a second one that takes that side, that side, that side, that side, that side, and so on. Here's a third one. Here's a fourth one. Here's a fifth, sixth, seventh, eighth, ninth, 10th, 11, 12, 13, 14, 15, and 16. So right here we see that that top layer has 16 of these cubes that we started with. Well, that's great. That's not everything. Well, let's write that. Top layer has 16 cubes, meaning 16 of the cubes we started with. How many layers are there? Each layer is going to have the same number since this is a cube. There are 4 layers. There are 4 layers, so how many cubes do we have? We started with 1 cube, we scale up by a factor of 4, we got this big cube, and now inside that there are 16 times 4, which equals 64 total 2 by 2 by 2 cubes. So right here, scaling by a factor of 4 resulted in 64 total cubes. How does that relate to the linear scaling factor? Well, 4 cubed is 64, and that is a theorem. So we have as a theorem, the volume of a scaled up object goes up in proportion to the cube of the linear scaling factor. And in notation, the volume is proportional to the linear scaling factor, which we'll call capital L cubed. So notice the volume goes up faster than the area went up, because the volume went up proportionally to the scaling factor cubed, and the area went up to in proportion to the scaling factor squared. And cubing goes up faster than squaring. So the next question is, we looked at volume and area. What about surface area? So what about surface area? Well, let's look at an example. Let's this time take a 1 by 1 by 1 cube. A 1 by 1 by 1 cube. What is the volume of a 1 by 1 by 1 cube? The volume is 1. What is the surface area of a 1 by 1 by 1 cube? Well, what is a cube? A cube has 6 surfaces. There's this side, and then there are 5 others. But all of the sides, we need to find the area of each side, and then add them all together. The area of each side is 1, because each side is a 1 by 1. So the surface area is 6 times 1. Well, that's great. Let's scale it by a factor of 3. Let's say we scale it by a factor of 3. So from the previous result, we know that the volume of this resulting object is going to be 27, because the volume goes up by 3 cubed. 1 times 3 cubed, 27. But let's look at surface area. Let's pretend this is a cube. Well, maybe I'll make it look a little more like a cube. Let's look at the surface area of this. We're scaling it by a factor of 3. So we have a 3 by 3 by 3. What is the surface area here? Well, the volume equals 1 times 3 cubed. We already know that. You could say it's 3 cubed from 3 times 3 times 3, or you could use the scaling factor and say it's 1 times 3 times 3 times 3, which is what that 1 is there for, using the scaling factor. What is the surface area? Well, again, we have a cube, so we have 6 faces on the cube. What is the area of each side? Well, this face is a 3 by 3, so that has area 9. This one also, it's a square. There, it's a cube, so all of these are going to have area 9. So we have 6 that have 6 faces that have area 9. So 6 times 9 is 54. So this new cube has a surface area of 64. Now, the volume went from 1 to 27. The volume went up by a factor of 3 cubed. How did the surface area go? It went from a surface area of 6 to a surface area of 54. So let's notice the surface area went from 6 to 54. So from that we can find the surface area, the scaling factor. Well, we could find how the scaling factor gives us a change in surface area. So the scaling factor for surface area that's an F, for surface area is 54 divided by 6, which equals 9, which happens to equal 3 squared. Now, the observation I'd like you to make from this can be recorded in the following theorem. As the volume is scaled up, the volume increases faster than the surface area. So in that previous example, we scaled it by a factor of 3. The volume went up by a factor of 27, but the surface area went up by just a factor of 9. So the volume went up much faster than the surface area. And in particular, how do they relate? The surface area, which we'll just call A, I'll say SA actually, I called it SA in the previous one. The surface area scales up in proportion to volume to the 2/3 power. So in that last one we had the surface area was 9. 27 to the 2/3 is 9. Why is 27 to the 2/3 9? 27 to the 2/3 equals the cube root of 27 squared. (27 squared), I don't know that. Actually, I do, because I actually talked about it in my calculus class. 27 squared, let's say you don't know what that is and then how to take its cube root. Instead of doing it like this, you could do the cube root of 27 and then square. The cube root of 27 is 3. 3 squared is 9. But the important thing to take from this is as you scale a volume up, the volume increases much faster. It's a very important, much faster than surface area. It's a very important result in geometry and scaling. So I'd like you to understand that using examples like we saw. I think it's easiest to see with examples.